Domain and range. Our objectives are to find the domain of a function defined by an equation, write the domain and range using standard notations, find domain and range from a graph, give domain and range of toolkit functions, and graph piecewise functions. Recall that the set of all possible inputs for a function is called the domain, and the set of outputs is called the range. How we write sets that make up the domain and range of functions often depends on how the relation or function are defined or presented to us. For example, we can use lists to describe the domain of functions that are given as sets of ordered pairs. Identify the domain and range of the following function. f of x equals the set of 210, 310, 420, 530, and 640. We know that the domain is going to be the x value of each of those points. This is in roster notation, so we'll go ahead and write our answer in roster notation as well. 2, 3, 4, 5, and 6. No matter what order those numbers are in, you'll want to make sure that you put the order of your numbers in here in numeric order, smallest to greatest. The range is the set of all of the y's. So we have 10. It occurs twice, but we only need to list it once since it's a unique element. 10, 20, 30, 40. If we are given an equation or graph, we might use inequalities or intervals to describe domain and range. With interval notation, we write the leftmost number of the set followed by a comma and then the rightmost number of the set. Then we put parentheses or square brackets around the pair depending on whether those two numbers are included in the set. Sometimes we even use one parenthesis and one bracket. A parenthesis means the number is not included in the set, but every number higher than it is included in the set. And a square bracket means that the number is included in the set. Complete the chart. For the graph on a number line, a parenthesis is used in place of an open circle, and a square bracket is used in place of a closed circle. Here our inequality is x less than 2. When we graph this, we can just graph the boundary point in question, and we know x is less than 2 should be shaded. So we're going to shade to the left of 2. We're going to put an arrow to indicate that that continues in that direction. And on the 2, we're going to use a parenthesis because that number 2 is not included. In interval notation, then, we can read this from left to right to be able to see what the interval notation is. We've got negative infinity to 2 with a parenthesis on the 2. We'll always put parentheses on infinities and negative infinities. Here, negative 3 is less than equal to x is less than equal to 5. I'll draw my number line. Again, it's not necessary to write a whole lot of numbers, just put the endpoints on there in the order that they appear on the number line. And we're literally shading x is between the negative 3 and the 5. So we're shading numbers between negative 3 and 5. Now, dealing with the boundary points, this is including the boundary because x can be greater than or equal to negative 3. So I'm going to put a square bracket, and I'll turn that bracket to where it's facing towards the shading. Here, again, I'm including the 5 as a boundary. So I'm going to put square bracket on the 5, and have that bracket facing the shading. Then interval notation is from -3, with -3 being included with a square bracket, comma, 5, and then a square bracket showing that the 5 is also included in the set. X is greater than equal to -1. So we'll graph just -1 on the number line, and we're going to shade numbers that are greater than -1, putting an arrow to show that that continues, and then we'll have a square bracket on the -1. In interval notation, we have -1 to positive infinity. -1/2 is less than x is less than equal to 3. Again, let's go ahead and graph the number line. We'll put on there a -1/2 and a 3. And x is literally between -1/2 and 3. So our shading is between -1/2 and 3. We're not going to include the -1/2, so we'll put a rounded parenthesis, and then the 3 is included, so we'll put a square bracket. It may help you to remember that with the equal to part over here on the less than equal to, it's part of an equal sign, and with a square bracket you can see there's kind of an equal sign hidden in that symbol. Just one way to keep those straight. So our interval notation is from -1/2 with a parenthesis and a 3 with a square bracket. Now, with the next few problems, we are to go from the graph and get the inequality and interval notations just from the graph. I know with this first graph I have from 1 to 5. 1 is the leftmost number, 5 is the rightmost number, but neither one of the boundary points are actually included. We're getting infinitely close to them, but we don't actually include the values of 1 and 5 in the set, so we'll use parentheses on this. And this is an inequality notation where x is between 1 and 5. X is greater than 1 and less than 5 at the same time. With this next set, we have shaded from 2 to 7. The leftmost number is 2 and the rightmost number is 7, where we're including everything in between. And I'm including the endpoints here. So we'll use the square bracket to indicate the endpoints are included. And here I'll have 2 and 7 on either side of the x. And I know that x is greater than or equal to 2 and less than or equal to 7 at the same time. Next set is from -3 to -1. My leftmost number is -3, the rightmost number is -1, and I'm not including the -3, but I will include the -1. So a parenthesis on -3 and square bracket on -1. In inequality notation, that's going to be -3 and a -1 on the ends. X is between those, and x is greater than -3 and less than equal to -1 at the same time. On the next set, I'm starting with the leftmost number of 5 and shading to positive infinity. Again, parenthesis on any infinity that we have. With this set, 5 is shaded in, so it is included. In inequality notation, it's going to be x greater than or equal to 5. With the next set, my leftmost is going to be from negative infinity, and the rightmost is 0, but I'm not actually including the number 0 because it's an open circle. In inequality notation, this is going to be x strictly less than 0. This next one is showing that everything on the number line is included. So we go from negative infinity to positive infinity. In inequality notation, we could say all real numbers and that's it. If we wanted to put it into set notation, you could use a double-spined capital R, and that would be signifying the real number set. Determining domain and range from a graph. Because the domain refers to the set of possible input values, the domain of a graph consists of all the input values shown on the x-axis. The range is the set of possible output values, which are shown on the y-axis. Keep in mind that if the graph continues beyond the portion of the graph that we can see, the domain and range may be greater than the visible values. To determine the domain, you look at the graph from left to right. To determine the range, look from bottom to top. Find the domain and range of the graph. Write your answers in both interval notation and as an inequality. Let's first look at the domain. One way that we can look at this is by rolling a pencil from left to right and reading off of the x-axis the values that we have, because domain has to do with what x values occur. It looks like the first x value we pick up is -3, and every point where this pencil is touching has an x value. Those are all made up of x and y values. So of course, we have many x values as we're going, and the last value that we see is 2, but it is an open circle. So as far as x goes, we are getting infinitely close to a value of 2, but we don't actually reach the number 2. So in interval notation, we're going to say that the domain goes from -3 with a square bracket and ends at 2 with a parenthesis to show that it's not included in the set. In inequality notation, again, x lives between -3 and 2, but x is greater than equal to -3 and at the same time strictly less than 2. Similarly, when we're trying to find the range, we can help focus our attention by using the same rolling your pencil technique. But again, with range, we're looking from bottom to top. So we're going to take our pencil and roll it from bottom to top, and it looks like the first number that we see is -5 reading off of the y-axis. Remember, range is all about what the y is. So I have -5, and it is a solid filled in dot, so we can use a square bracket there, and we move the pencil up, rolling it, rolling it, rolling it. Now this is concerning. I have an open spot here, at the x value of 2, but remember that this is about the range. Do we have a y value on this green line? And we certainly do. We have a solid dot over here, a solid place in our graph, so we know that the value of y being 0 actually is covered, so there are no worries there. We continue rolling the pencil up, rolling it up, and it looks like the last value that we have a y for is at 4. And is that point included or not? It is included. It is included because even though it's not a big round bulbous dot like this one, it is a solid dot. In fact, every piece along here is a solid dot until you get to this open circle right there. So we're going to use a square bracket there, and in inequality notation we're going to go from -5 to 4. Our y values lie between -5 and 4 and are inclusive. Y is greater than equal to -5 and y is less than equal to 4 at the same time. Now, given a function in equation form, how do we determine the domain? They may not have given us a set of numbers in roster notation, and they have not given us a graph. So let's think back to our two restrictions. So far for us we have two restrictions, and those are fractions with variables in the denominator. It is possible to use an x value for your domain that causes the denominator to equal 0, and then your function would be undefined. So we want to restrict the domain so we're not using those values. In fact, we state the domain restriction in algebra as the denominator cannot equal 0, and then we solve that inequality. In this way we find the inputs that are excluded from the function. When we have radicals with an even index, there is another restriction. We state the domain restriction in algebra as the radicand is greater than equal to 0. That's just a fancy word here for the guts of a radical. And then we solve that inequality. Remember what kinds of things you can take the square root of. You can take the square root of 0. The square root of 0 is 0. You can take the square root of positive numbers. Those will be real. But if you take the square root of negative numbers, you'll get thrown imaginaries. So this is the reason for the radicand greater than equal to 0 restriction. In that way we find the domain of the function. Now, when working with functions that are used with real-world applications, you'll need to consider what input values make sense in the context of the application. So let's do a bit of practice. Find the domains of the functions and state them in interval notation. Part A, f of x equals x minus 1 over x squared minus 4. The restriction on this function is that it is a fraction where we have variables in the denominator. So the problem lies in the denominator. We want to make sure that x squared minus 4 never equals 0 because we don't want to divide by 0. We go to solve this. X squared cannot equal 4. We're going to take the square root of both sides. Remember, we're solving, so when you put the square root on that, you have to put the plus minus as well. So x cannot equal plus or minus 2. Let's see what this looks like as a graph so we can picture what to put in interval notation. Here's -2, here's +2, and as long as x is not either one of those numbers, we're okay. We can use numbers over here We can use numbers in between, and we can use numbers over here. So our domain in interval notation is negative infinity to negative 2, union negative 2 to 2, union 2 to positive infinity. In part B, our function is y equals square root of 7 minus 5x. The restriction here is that we have a square root. The radicand of 7 minus 5x must be greater than or equal to 0 for us to have a real result. So we write that inequality and solve it. Negative 5x is greater than or equal to negative 7, and x is less than or equal to 7/5. Notice that the inequality sign flipped. The inequality sign flipped because at this part of the problem we divided both sides by negative 5, and that flips the inequality because you have negated a directional statement. So now x is less than 7/5. Let's go ahead and graph 7/5 on the number line. X is less than that or equal to. So our domain in interval notation will be negative infinity to 7/5 with a square bracket. With the same directions of finding the domain, we're looking at problem C. F of x equals 3x squared minus 4x minus 1. Remember, we don't really want to just look at what x can be. That's what domain is, but we want to think about what the restrictions are. We have two restrictions: fractions with variables in the denominator and square roots. Those are the only two restrictions that we have so far in algebra, and this has neither of those restrictions. Therefore, our domain is going to go from negative infinity to positive infinity. Okay? So you don't really show any work on this. You just think through what the restrictions are. If it doesn't have those restrictions, then the domain is all real numbers. In g of x, we have x plus 1 over 2 minus x. The restriction here is that we have a denominator with a variable in it, and that cannot be equal to 0. We cannot divide by 0. So we solve this inequality, and x cannot equal positive 2. Picture this on the number line. Here's 2. X can be anything but 2. So we end up with a domain of negative infinity to 2, union 2 to positive infinity. Our next problem with the same directions to find the domain, we have h of x equals x plus 28 over x minus 2 times x plus 5. And I know my restriction is that x minus 2 times x plus 5 cannot equal 0. We don't want division by 0. So we use the principle of zero products. X minus 2 cannot equal 0, and x plus 5 cannot equal 0. So x cannot equal positive 2, and x cannot equal negative 5. So let's get this on the number line, make it easier for us to get it into interval notation. Make sure you place those numbers on the number line in the order they actually appear in the number line. We know that x cannot be either one of those, and we have all the other numbers that we could use available to us. The domain is going to be from negative infinity to negative 5, union negative 5 to 2, union 2 to positive infinity. Here at f of x, we have the square root of 2x minus 3. Well, I know that 2x minus 3 must be greater than or equal to 0 because I'm taking a square root, and I can only take square roots of positive numbers or square roots of 0. I solve that inequality. X is greater than equal to 3/2. And then I have my number line. Here's 3/2. And if you want, we can use square brackets like we've done in the past. And that translates a little more seamlessly with our interval notation, starting at 3/2 with the square bracket to positive infinity with parenthesis. Next, we'll take a look at piecewise defined functions. Sometimes we come across a function or some kind of behavior that we're trying to model that requires more than one formula to obtain the given output. A piecewise function is a function in which more than one formula is used to define the output over different pieces of the domain. They'll look similar to this. F of x equals, a curly brace will open. They'll have one formula if x is in a certain domain, another formula if x is in another domain, and maybe another. Here we have an example of a piecewise function in h of x. We see we have 3 parts and different domain restrictions on using those parts. The way I like to graph these, and you will want to graph these on paper, don't just choose the graph that's given to you in homework. Since I have 3 parts, I'm going to make 3 different t-tables. And in those t-tables, I'm going to use the boundaries that are shown in the domain. This is from -2 to 1. And I look here at the type of function. It's not a linear function. So I need to make sure that I have more points in there to give me an idea of what the curve will look like. Now let's also notate what the endpoints will be. That -2, because it's greater than or equal to -2, is going to be a solid dot when we graph it. This, being a strictly less than 1, is going to be an open circle. Let's go ahead and run our function. -2 put into the h of x function we put in here. -2 squared is 4. 4 minus 4 is 0. -1 squared is +1. Minus 4 is -3. Put in a 0. That's 0 minus 4 is -4. And let's put in a 1. 1 squared is 1. Minus 4 is -3. Before we lose focus on what we're doing, let's go ahead and graph this piece. I have -2, 0, and it's an closed circle. I have -1, -3, 0, -4, and 1, -3, and that is an open circle. When I connect those pieces, it's part of a parabola that's including this end but not including this end. The next piece is -2x plus 5 if x is between 1 and 3 inclusive. So in our t-table we can put 1 and 3 as the boundaries. Now this is just a linear graph, so we just need the 2 points, but just to be sure and have a check, I can also put 2. 2 is between 1 and 3, so it's in the domain of that piece. Again, let's go ahead and notate to the left of the table whether the boundary points are included or not. Since we have here equal to on both of those endpoints, this means we're going to include both of the boundaries. Let's put 1 into the function. I have -2 plus 5 is 3. Put in a 2. I have -4 plus 5 is 1. Let's put in a 3. I have -6 plus 5 is -1. Again, before we lose track of what we're doing, let's come over here and graph that piece. I have 1, 3 with a solid dot. I have 2, 1, and I have 3, -1. And that's a solid dot as well. Definitely, this is just a straight line, and we have a good sketch of it there. Our last piece is that the function is going to equal 2 if x is greater than 3. Again, this is strictly greater than 3, but you must use that boundary point in your table. Okay? And then pick numbers that fit that condition. Pick x's that are greater than 3, maybe 4, maybe 6. Now, we know that we cannot be equal to 3, so we're going to notate to the left of the table that this is going to be an open circle once we graph it. And when we plug that into the function, out comes 2 every time. I'm going to go ahead and graph this. 3, 2 with an open circle. I have 4, 2. I have 6, 2, and this can continue. And I end up with that constant function. So we have an example here of 3 different types of the parent functions with restricted domains in there. A good example here of a piecewise function and a practical situation in life. We have a cave that charges $7 per person for a tour with a group of 1 to 11 people, or a fixed fee of $84 for a group of 12 or more people. Let's write the function relating the number of people n to the cost c. So we have the c of n. N is the number of people. So we're going to have restrictions on the domain based on the number of people. So if we have between 1 and 11 people, then we're going to be charged $7 times each person. Or we can have a fixed fee of $84 for n greater than or equal to 12. That does it for this lesson, so you can go ahead and start your homework.